All right, so we are back for round 2 of the chi-squared test. And I just have a quick reminder to keep us on track for what is the purpose of this test that we are doing. Try to remember from the beginning of this conversation when we first started talking about chi-squared, what is the purpose? Why are we doing this statistical test in the first place? Well, it has to do with this idea of the null hypothesis. And what we are trying to do is remember, we are trying to determine if our values are statistically different from the expected values based on our expected phenotypic ratios, right? That's what we're trying to do, specifically with this cross. Now, if you did the calculation from the last video, hopefully you were able to calculate your chi-squared value of 0.818. All right. So now that we've determined our chi-squared value, there are 3 other values that we are going to need to determine in order to complete our chi-squared analysis. That's the degrees of freedom, the alpha value, and the critical value, right? So your degrees of freedom is the next step in this process. When you're analyzing degrees of freedom is the number of potential outcomes minus 1. All right. So when we're looking at our scenario with the black and white and short and long-haired rabbits, how many different expected and observed outcomes are possible for this calculation? Take a second to think about it. Well, if you think about it, all of these values, if we're thinking about the number of possible outcomes, we have 4 different possible outcomes. Remember, we have short black hair, short white hair, long black hair, and long white hair. So we have 4 possible outcomes minus 1, which means our degrees of freedom is going to be 3. Okay? Pretty straightforward. Now let's determine the alpha value for our scenario. All right, so the alpha value is the probability that our test will provide us a false support or refute of our null hypothesis. Now, usually in an equation, your alpha value will be given to you. They will tell you you will have an alpha value of 0.5. I have yet to see an example where AP Bio did not specifically give you the alpha value, all right? But you don't always get an alpha value of 0.05. This one is the most common. So if you are not given an alpha value, which I have seen frequently on AP Bio tests, if you are not given an alpha value, assume it is 0.05, which what it correlates to is essentially a 5% chance that our test gives us the wrong results, right? Now, you can have variations in your alpha values. You can have an alpha value that has 0.01, which gives you a 1% chance that our test gives us the wrong result. What this essentially correlates to is the accuracy of your test. If you have a lower alpha value, that means your test is going to be more reliable. It's going to be more accurate. This one is considered accurate enough in most experimental questions. 0.05 is considered accurate enough usually. So in this case, our alpha value that we're going to use is 0.05. Always assume it's 0.05 unless otherwise specified. So what this means is using an alpha value of 0.05, there is still a 5% chance that something outside of Mendelian genetics is affecting our data, but the numbers do not necessarily accurately reflect that. So that's what a 0.05 alpha value means. Now, what's our next step? Now we have to look at the chi-squared table. Again, don't get intimidated by this. It's pretty easy to read. All you need to do is look at the degrees of freedom and the alpha value to then determine your critical value. So your critical value is going to be one of these numbers in the table, all right? Your degrees of freedom are indicated on the left-hand side. Those are your degrees of freedom. And then your alpha values are indicated on the top of the table, right? So hopefully you guys have an idea. You can start to see where our value is going to lie, right? We are going to be using a 0.05 alpha value, and we already said that our degrees of freedom is 3. So our critical value, hopefully you figured it out, our critical value is going to be, oops, already got there, 7.814. That's going to be our critical value, right? Now, our critical value, what does it mean? It's essentially the value that we compare to our chi-squared value to determine if our data is close enough to our expected data based on the number of outcomes and our desired confidence in our data, our alpha value, okay? It's a comparison tool. Don't get bogged down in the details of this if you don't understand it. For those of you that are interested in the statistics of it, this is what the critical value means. But you don't necessarily need to understand this in order to understand the outcome of a chi-squared test, which we are about to unveil, right? Now, this is step 5, and this is where students tend to get stuck or forget how to do this step, okay? Now you need to determine, is your chi-squared value greater or less than the critical value, right? So this is our chi-squared value that I just circled in blue. And in green, I'm going to circle our critical value. So we're trying to determine, is our chi-squared value greater or less than our critical value? I want you to try to answer that on your own. Because if our chi-squared value is less than our critical value, we accept the null hypothesis. However, if our chi-squared value is greater than the critical value, we reject the null hypothesis. So what are we going to do? Do we accept or reject our null hypothesis? Well, our chi-squared value is significantly less than our critical value. So because our chi-squared value is less than our critical value, we are going to accept our null hypothesis. Now, what does this mean? If we go back to our null hypothesis, we are trying to determine, is there a statistically significant difference between the expected and observed frequencies, right? That is our null hypothesis. There is no statistically significant difference between the expected and observed frequencies. And since we accept the null, that means that there is no statistically significant difference between the expected and observed frequencies. So we know that this seemingly sort of weird 289 falls within the boundaries of acceptable parameters for Mendelian genetics. So we know that there are no outside influences on these genes. We know that it is determined by regular Mendelian genetics. Now, there's still a 5% chance that it could be determined or it could be being manipulated by outside other non-Mendelian genetics mechanisms. However, it's only a 5% chance, and that is a statistical likelihood that we are willing to accept. Okay? So that is the chi-squared test. Now you should be able to complete the rest of the practice problems. You're going to notice on some of these practice problems that they ask you to fill out a chart. Now, let me see if I can open up that chart. Oh, this is the answer key. Let's see if I can open up that chart. So here's what that chart's going to look like. Now, the reason I did not teach you guys to use the chart is because on the AP test, they will not give you the chart for a chi-squared test. It is a helpful tool for learning chi-squared analysis. However, it is not something that you will be given on the AP test. So I did not teach it to you because I want you to be able to practice this in an attempt to answer the questions on the AP test, right? So use these charts as a tool, but know that you will not have access to them on the AP test. You can make them yourself. They're easy to make yourself, but you will not have access to them on the AP test. So you need to figure out how to calculate these values on your own. Okay. All right. Hopefully that was helpful, and I will send you guys another video soon.